We are now recording. So let's start from the current slide. Okay, and this is where we left off last time. We had gone over that, and I was giving you a few examples of continuity of inverse functions. The deal here, let's go over this one more time just to remind ourselves what we're talking about here. Blow this up so it's easier to read. Okay. If f is a continuous function on an interval I with a range R, and if f inverse exists, and for that to exist, f must be 1-to-1 on some interval with range R. So they really should put that in there. But if f inverse exists, that would be only where f was 1-to-1. Then f inverse is also continuous, but now what was the range of f becomes the domain of f inverse. Okay? So I showed you two of these before. I was going to show you tangent this time. Okay. Now, to get the nomenclature right, let's start, and I'm going to call it g of x. We get my pen colored right. Okay. Oh, let me say this again. I did want to remind you of the thing, the Lady Day presentation by Red Mountain Theater is today at 1 o'clock on the Birmingham East Campus A.G. Gaston Auditorium. Okay, I wanted you to know that. And then the other things about graduation applications and notifications, that you know about that already. All right, let's say g of x is equal to tangent x. So let's just for funsies plot what tangent x looks like. Can you tell me anything about tangent x? Okay, makes that sort of snaky curve there. What are the limits of its domain? Pi, minus pi halves to pi halves. Minus pi halves to pi halves is the limit on the domain. Those are vertical asymptotes, which I sort of like to write in red, just so you know you can't ever touch them or cross them. Okay. Now, what else do you know? I saw you draw your finger in the air, so I think I know. At zero, it's zero. Now, here's another data point. At pi fourths, tangent is 1. Okay, and negative pi fourths is minus 1. So with those three data points, you get the general idea that's what tangent looks like. Okay? Now, what we're interested in, let's do this in a different color. You pick a color now. Not red, not purple. Blue. Dark blue or light blue? Light blue? Okay. Baby blue, Carolina blue there. Okay. Now, what we have here is f of x, can you see that well enough? Okay, is equal to inverse tangent. Okay, now, one of the easiest things to do with, and by the way, I probably should have done this too. Let me go back and do this. Oh no, yeah. The domain of g would be negative pi halves is less than, not less than or equal to, you want to make this, yeah, we called it x, less than x, and that's less than pi halves. It can't be equal to, that's the vertical asymptote, can't be there. What's the range of g? Infinity, negative infinity to positive infinity. I'm just going to write that in interval notation, negative infinity to positive infinity. A little easier to write that way, okay? Now, let's go back to our baby blue. And one of the first things, and this is what the theorem says, the domain of f, the inverse function, is now what the range of the other was. That's negative infinity to infinity. But the range of f, that's now negative pi halves to pi halves. I don't like writing that one that way, but it's just easy to write. Okay? So that means we come up here. I think I'll do, well, let me go back a second. Right, yeah. The domain is between the reds here, minus pi halves to pi halves, and the range is minus infinity to positive. It keeps on trucking both directions. So then for f, which is the inverse function, these reverse themselves. The domain is what the range was, and the range is what the domain was. Okay? So that means, yeah, what I was going to do here is tick in my minus pi halves here. I'm sorry, that's positive pi halves, minus pi halves here. And then put my now they're horizontal asymptotes, okay? But unlike some horizontal asymptotes, you can't touch across these. You have to stay in between them. And my data points, and I'll put these in the baby blue, 0, 0 is still a data point. You're just reversing the coordinates. But now, this one that was pi force 1 is now 1 pi force. 1's out here, and pi force is up there, okay? And negative 1 be somewhere about there, and pi force would be here, okay? So basically, this function looks like this. Oops, it doesn't have a wrinkle in it. I bumped into something. So basically, you've taken that and flipped it. Now, interestingly, right in this area here, that's almost your identity function. You know, y is equal to x. And so both of those line pretty close to each other there. Now, I don't have them drawn well, but they line pretty close. But this one approaches there, this one's approaches there. So they do diverge after a while, but that's what the inverse tangent function looks like. Domain, all real numbers. Range has to be between minus pi halves and pi halves. And it looks a lot like your tangent function, only it's sleeping. It's laying on its side, kind of. It's flipped and slept, okay? Yeah, exactly, yeah. And notice also, this is a strictly increasing function there. It has to be one-to-one. And this is strictly increasing here. It's just that this is increasing extraordinarily rapidly here, slower here, extraordinarily rapidly, awfully slow here, ordinary here, awfully slow there. Yeah, it just flips over. Say that again? No, it can't. It cannot, because the inverse tangent is not defined in its range for minus pi halves or pi halves. It approaches it, but never can touch it. Yeah. So I may should have done 2 graphs, but I thought maybe my graphs are so ugly that it might be hard to pick up. Okay. Now, the next theorem we hit, I hope this is the 10 o'clock siren, right? Just a test. Okay. So let's move on to theorem 5. There's a little free words. Finally, it's important to know that a composition of continuous functions is again continuous. And the following theorem is proved in Appendix D. I know you're going to run right over there and read that proof, but yeah, I'm not sort of teasing a little bit, but yeah, it's worth looking at. Okay, here's theorem 5. Let's say that G is a continuous function at x equals C. Of course, you know what that means. All around x equals C, it's continuous, you know, it's all connected there. Now, F is also continuous, and it's continuous at not C, but G of C, okay? Because we're going to be taking the composite of that. So x is the independent variable for your G function, but the output of the G function is your input for the x function. That's what composite functions do. So your bigger function, capital F here, is a little f evaluated at G of x. Okay? Which means give me an x, any x. I'll first evaluate G at that x, and as long as that x is close enough to C, it's going to be continuous around C. So that will give me a value, guaranteed, some value, G of x. And then that value, I'm going to operate on that with F, and F has to be continuous around that G of C, that value, the output for G. So therefore, the composite function, capital F, is also continuous at x equals C, around x equals C. Okay. What's that? No, not quite. Okay. Yeah, I think the next example will show what we're talking about there. Yeah, let's do that example, and then if you have a question, because I'm not sure what your question was, but maybe this will answer it. Okay, I'm going to go back to a dark color here, dark purple. Okay, here's the example. Here's your f of x, capital F of x. It is the function x squared plus 9 to the 1/3 power. Okay. Now, in this, what would you say your little g is? What would you say your capital F is? To use the terminology from here, what would you say little g of x is? Okay, close. X squared plus 9. Think of this. Here's how I think of it. The g is inside the parentheses of little f. What's inside the parentheses here? That's your g. Your g of x would be x squared plus 9. Now you could have it, break it down and do smaller, but this, okay, that's x squared plus 9. Now, tell me, is that a continuous function? Here's the dead giveaway. It's a polynomial function. All polynomial functions are always continuous. Not just continuous, smooth and continuous. Polynomials are great functions to mess with because they're always smooth and continuous. Okay. Now, I think maybe what you were just talking about there, I'm not sure, but we also have to have that being a one-to-one function. Now, what that is, that's a parabola. Okay? Let's think back. If you just had x squared, I know that one. That goes through the origin here, and 1, 1, minus 1, 1, 2, 4, minus 2, 4, 3, 9, minus 3, 9, 4, 16, minus 4, 16, 5, 20, yeah. So it's that parabola that does like this. That's without the plus 9. What does the plus 9 do? 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a vertical shift upward. Now that's my vertex, and it's there, there, know it looks something like that. But that's not a one-to-one function. It's only one-to-one from 0 to positive infinity or from negative infinity to 0. But it can't cross 0 because then it backs up on itself. It fails the horizontal line test. So this function is continuous everywhere, but it's not one-to-one everywhere. Only one-to-one for 0 to infinity or infinity to 0 or any smaller part of that. You just can't have something right and left to 0 because it's not going to be there. But it is continuous. Okay. Now your f function then would be the, and I don't like to use the same variable, but they do. Your f function, if it's okay, I'll use f of y just so it won't be as confusing. F of y would be that g function, which we're going to call y to the 1/3. It's the cube root function. Now the cube root function, I hope that you realize is a function. Remember, square root function is like this. It just keeps on climbing. The cube root is a lot like that, but it keeps on climbing, but it does a little wiggle around 0. Because you can't take the cube root of a negative number, you can't take the square root of a negative number. But that's also a continuous function everywhere. And it's also a one-to-one function everywhere. When you take the cube root of a negative number, you get a negative number. Cube root of 0 is 0. Cube root of positive is positive. Never backs up on itself. So that is a one-to-one. Now, they don't say anything about that, but that's what it is. So G is continuous everywhere. F is continuous everywhere. Then the composite function is continuous. And this is not talking about anything else. It's continuous everywhere. Why did I get onto a one-to-one? Because to go do the inverse. We're not doing the inverse yet. So this function is continuous everywhere. The F, capital F is because G is and F is, little f is, therefore the composite function is continuous everywhere. Now, and when they write it, they write x's in there. And math books have started doing that, but man, I found that, I'll do it because the book did, but I found it a little confusing. It really isn't, but to me it would be more straightforward if you put y's in there, okay? But that x and f is not the same as the x and g. What the x and f is the g, not the x, but the g. So, because that's what you have here. This thing raised to the 1/3 power. Okay, so the composite would be a continuous function. They're not talking about one-to-one functions or inverse functions yet. They were earlier, but now we're just talking about continuity. Okay. Now, I'm sorry I got off on the inverse. That's what we were doing in the last theorem, but not in this one. Okay. Now, here's another one. F of x, and here again, I wish they would use a different variable so you don't think it's the same function. It's not. This f of x is cosine of 1/x. Okay. Now, our little runner or dancer or whatever. Okay, yes. He's back. And you know what? I forgot to mark the roll anyway, so I'm glad he came in for other reasons too. But Samaria was here already, and now Richard is here. Double the class size, just in one fell swoop. Okay. Okay. We're on page 80, theorem 5. Okay. We're looking at composites of functions. What would be the g of x in this case? In other words, the g of x is the innermost function.
So the x to the negative 1.
Exactly, x to the minus 1. And what would your f of x be? The little f of x. Cosine x. Okay. Actually, I prefer to put y's in there, but the book uses x's, so I use x's. Now, the question is g of x continuous? Remember, for the composite function to be continuous, g of x must be continuous, and f of x must be continuous. That's what it says here. Okay? Is g of x continuous? Where is it not continuous? Right, what does that mean? Yeah. Just realized I've got a big tangle in my hair. Okay, no, I don't have it all. I don't know what that was. Okay, here's the other way to write that. 1 over x. That's what x to the minus 1 means.
So just at 0?
It's not continuous at 0. You cannot take 1 over 0. So it's continuous for all x's greater than 0 and for all x's less than 0. So from negative infinity to 0, but not counting 0, and from 0 but not counting 0 to positive infinity, either of those two domains, this would be a continuous function. The g of f of x, cosine x, is continuous everywhere. No sweat there. But the g of x limits where the continuity is for the capital F to the same limits that it is for g of x. Okay? Not equal to 0. Okay. So when they say here, if f is continuous at x equals c, in other words, this c cannot be 0, okay? Because g is continuous everywhere is that. So if g is continuous at 17, at minus 4/3, at pi over 3, it's everywhere except at 0. So if it's continuous at x equals c, any value not 0, and f is continuous at those values, and f is continuous everywhere, little f, then the composite function, capital F of x, is continuous at that c, as long as the c is not 0. So that's all it's saying. Okay. Now, here's another capital F. Had it, but I've lost it. There it is. Okay. Capital F of x is 2 to the sine x. Okay? Now you tell me, what's your F function there, or your G function there? Say again? Okay. Think of it this way. It's a thing inside the parentheses. That would be the sine x. Okay, and then your little F function would be 2 to the x, exactly. Okay? So, what about the continuity of sine? Everywhere. Okay? How about the continuity of 2 to the x? Everywhere. Okay? 2 to the 0 is 1. 2 to the any x. Minus 1, that would be 1/2, plus 1 would be 2, yeah. So F is continuous everywhere, G is continuous everywhere, so your capital F is continuous everywhere. Okay. Now, a little definition here. You got your books. No, do you have one yet? Huh? Oh, you got it, okay. In the book, it says, moreover, an elementary function, this is sort of a definition here, is a function that is constructed out of basic functions using the operations of addition, subtraction, multiplication, division, and composition. Okay. Since the basic functions are continuous on their domains, an elementary function is also continuous on its domains by the laws of continuity. Here's an example of an elementary function. think I'm going to go to a clean page for this one. It's a little complicated looking, but it's okay. Here's your capital F of x. They tell you it's an elementary function, okay? Inverse tangent of x squared plus cosine of 2 to the x plus 9 divided by x minus 8. Okay. Talk about a function. Is that not a fun one? Okay. Now, that function, the elementary function, which is made up of all these other functions, okay, where is it continuous? Or let me say it another way. Where is at least one place it's not continuous?
Positive
8. X cannot equal 8. Absolutely. Because the thing in the parentheses has no meaning there. Okay? Now, that's at least one. Okay? Does this bother you any? No, even an 8 would be okay there. 2 to the x is continuous everywhere. Positive, negative, fraction, decimal, rational, irrational, doesn't matter. Cosine is continuous everywhere. X squared is continuous everywhere. Okay? Now, your inverse tangent, if you remember that, its domain is everywhere. Its range is limited, but its domain is everywhere. So yeah, no problem there. The only thing in that whole deal is this, that denominator can't be 8. The denominator can't be 0, that means x can't be 8. So therefore this elementary function, that doesn't look very elementary to me, okay, is continuous everywhere except x equals 8. Okay? See, if this had been a tangent here, you've got big problems. Okay? Because what's in your argument here can't be any of your half pies. Okay? So then you have to deal with all that. Thank you for not doing that. The only thing that you had to deal with was that denominator. Okay? Good deal. Now, all that to get you to this. It is easy to evaluate a limit when the function in question is known to be continuous. In that case, by definition, the limit is equal to the function value, which, I guess I ought to write that down here too. The limit, now, as x approaches c, of f of x is f of c. Oops. Now, that's true when f is continuous at c. If f is not continuous at c, no. You can't say it. But if f is continuous at c, or c and everywhere close to c, then that will be true. Okay? And that's called substitution. Plug it in, you know, and see what you get. Now, if it's not continuous there, it may still exist, but you have to figure out what that limit would be. Okay? That's called the substitution method because the limit is evaluated by plugging in the value x equals c. So let's do a couple of those. Oh, let's go on and clean the page. Okay? You need that any longer? Okay. Example 3. Evaluate A. The limit of, as y approaches pi thirds, of sine of y. Evaluate the limit of sine of y as y approaches pi thirds. Any guesses? First thing you do, you say the sine of continuous function is especially around pi 30. Yeah, sine's continuous everywhere. All real numbers, so no problem there. So what do we do? Plug it in, and that's where you're having your problems, right? What is sine of pi thirds? Okay. I'm going to remind you of a little trick here. I know one of you should remember this, but, okay. If you go back to the unit circle or any circle, this is y equals 0, y equal pi 6. Now this isn't the y-axis here. This is y is equal to pi fourths. This is y is equal to pi thirds. And this is y is equal to pi halves. Okay? When you're evaluating these values here. Now, the sine is the vertical value. Okay, I don't want to use y because we're using y here. Let me tell you what those are now. A little bit of review. At 0 here, you have the square root of 0 over 2. I know that's a dumb way to write it, but I'm doing it. This is the square root of 1 over 2. This is the square root of 2 over 2. This is the square root of 3 over 2. And this is the square root of 4 over 2. It's just a little mnemonic device to remember those our favorite angles. Okay? 0, pi 6, pi fourths, pi thirds, and pi halves. For the sine, it just goes up. Well, the square root of 0 is 0. Okay, so that's just 0. Square root of 1 is 1, so that's just 1 half. But for pi fourths, it's square root of 2 over 2. That's it. It's done. And for pi thirds, it's the square root of 3 over 2. That's what we're looking for here. Square root of 3 over 2. And for pi halves, that would be the square root of 4 over 2. What's the square root of 4? 2 over 2 is 1. Yeah, we knew that. Okay, so that one is square root of 3 over 2. Now, you don't have to remember that little mnemonic device, but I don't know if that's what it really is, but to me, it's an easy way to remember signs.
I don't know. It's like no matter how many times I try, it's always so cool to see that. You know,
Yeah.
Just how it increases by 1.
Right.
So square root of 0, 1, 2, 3. You know, and
Yeah.
then just all over 2, and then just
Yeah.
reduces down.
And then, to do cosines, you just start with 0
Go
there
up.
and go down.
Out of the way.
So then it's 1, square root of 3 over 2, square root of 2 over 2, 1 half, and 0.
Exactly.
So it just goes the other direction.
And then, if you know that side, you also know.
Yeah, you
the
know
other
all
side
4 of
if
them.
you, you know.
Yeah, if you change the signs of the x's but leave the y's the same,
Yep.
then you change both signs down here, and change the signs of the y's but leave the x's the same. Yeah.
Exactly.
Yeah. Or horizontals, I should be saying. All right, so that was the A one. Let's look at B. Little more involved here, but still not bad. The limit as x approaches -1 of 3 to the x over the square root of x plus 5. Okay? Now, it could be that you start having heart palpitations when you see the square root, because there your domain's limited, right? Well, you also have a variable in the denominator. There it's the domain's limited. But the only thing you're worried about is it continuous at x equal -1? X equal -1 gives you no problem there. And the square root of 4 is 2. That's not 0. No problem. Calm down. Okay? What would you do to evaluate that limit? Plug it in, plug it in. As long as it's not -5 or anything less than -5, that would make your inside here negative. You can't do that. Well, -1 is not -5 or less than -5. It's greater than that. So this will be Rodney's here. Okay? What's that? Almost what? I can't hear.
almost perfect.
Oh, almost, yeah. Actually, we added one more person, and he hasn't shown up yet, so we're not as far from it as we're further from it than we used to be. But okay. So what we do here? Plug it in, plug it in, and what do you get? 3 to the minus 1 over, and on the bottom you got a 2, because minus 1 plus 5 is 4. Square root of 4 is 2. What's 3 to the minus 1?
Is it just flipped?
Yeah, so that's 1/3 times 1/2, which is 1/6. You got it. Okay? And yeah, they got it too. Good for them. Okay. Now, here's one that most math books love. So I'm going to clear this. Everybody got everything you need there? I'll erase all the ink from the slide. And for those who did come in late, just a couple of small reminders. Lady Day is being produced by Red Mountain Theater Company on the Birmingham East Campus in the A.G. Gaston building today at 1 o'clock. Some of say again?
Are you going to be able to make it?
No, I've got class.
Yeah, class.
Yeah, so I can't. But you know, especially classes on Birmingham campus can easily make it, usually. But the ones out here, if you don't have class at that time, you, if you can, go to it. It's free to the public because Austin's already paid for them to do the production there. So anyone that wants to see it there. If you go to Red Mountain, you're going to pay. Yeah, but Austin paid for it to do here. Should be quite nice too. Okay, here's a function they love. Okay, let's see if they have the picture. Ah, there it is. I won't have to draw it. Good for them. Okay. Here is the greatest integer function. Okay. Interesting, their notation here. I had never noticed this before. Huh. The notation in the book is different from notation on the graph, on the display. The notation in the book leaves off this little wing here and there on top. It has it on the bottom, but not on the top. I had never noticed that until just now. I was going to say some text, like pre-calculus algebra, the one I teach from there, actually has a double line vertical with both of the things over. This one just has the bracket. Just using the bracket could be a little confusing because that's typically the notation for a matrix. But since it's obviously not a matrix, I think you can get away with it. But in your book, they leave off that upper wing. I don't know what you call that. I had just never noticed it till now. But this is the greatest integer function. The greatest integer when x is, say, -3, n -3 is -3. Okay, they didn't draw this circle here, but -2.5, it would still be -3. The greatest integer is you look to the left, and see the greatest integer that is within this value here. That would be this one, -3. When you get to -2, the greatest integer in -2 is -2. As you keep going this way, -1.9, -1.7, all like that. Still the greatest integer in that is -2. So all the way until you get to -1, then you jump up to -1. So these are open circles at this end, closed circles at that end. Greatest integer in 0 is 0. Greatest integer in 0.7 is 0. The greatest integer in 0.9 is 0. But the greatest integer is 1. So you jump up to that. Okay. Now, for positive numbers, it's a piece of cake. Just drop the decimal part, and you've got it. 1.7. The greatest integer in that is 1. It's just when you're on the negative side, you just have to remember you still look to the left. The greatest integer, first integer you look to when you go to look to the left, that's the greatest integer. So it's a stair-step function with the solids here and the open surface there. Okay? Now, It's not quite absolute value because you can't have negative values.
Well, okay. So I was trying to just. So what are the the brackets? What is that trying to?
It's just saying, rather than
You see what I'm saying?
yeah, the absolute value function tells you ignore the sign, just use the value.
Right.
Okay. This one's telling you ignore your fractional parts, your decimal part, just use the integer.
Got it.
That's what you're doing. The integer to your left. And that will work every time.
Okay.
Okay. So it's kind of, I guess, in that sense like that. Okay. Now, they just give some more examples of it. Okay? Now, here's the question. Example 4. Can we evaluate the limit? Sorry, I've got to. Can we evaluate the limit as x approaches 2 from the upper side of, now, I don't know which to use. The book uses this symbol, okay, absolute greatest integer in x, okay. The slide uses a bracket, and other texts use a double line with a bracket. I'll do what the book is doing. Can you evaluate that? And can you evaluate the limit as x approaches 2 from the minus side of the same thing, greatest integer in x? Okay? So let's go first from the plus side. Greatest energy is that x is approaching 2 from the upper side, from values greater than 2. What's his limit? As x approaches 2? 2. You're right. Okay. So that one's 2. Helps to have the graph here. But as x approaches 2 from a lower value, below 2, that would be somewhere down here. As you're approaching 2 from there, what's your limit? 1. Doesn't equal 1. It doesn't get to 1, but it approaches 1. Because it's 1 everywhere, close to 2. From the left, it's 1, 1, 1, 1, 1. Now when you get to 2, it jumps up. But if you're approaching just from the left, it looks like the limit is 1. Now, is that a continuous function? Obviously not. It's a step function. It has discontinuities everywhere. Okay, here and here, I mean, all the integral values. So it's definitely not. And at these. Now, if you had absolute value of x where x was 0.3, yeah, it's continuous around 0.3 or negative pi thirds or anything other than an integer. Then yeah, it's continuous around that, and you can take the limit and plug it in. But at those places where you have a discontinuity, no, you can't. Okay. Conceptual insight here. Real world modeling and continuous functions. This is a pretty nifty thing here. Okay. No. You have to hit the right button in the right order or it screws up. Okay. Okay, there we go. Now, I teach physical science. I found this interesting. I've not seen this graph in my physical science book. This is pretty neat, okay? Our atmosphere is broken into different ranges, I guess you would say, from somewhere above the Earth, obviously not at elevation 0. This is altitude in kilometers. Obviously, they've skipped some space here, somewhere up there, and this looks like to me to be about maybe 2 200 meters or something like that. Somewhere up there, you enter what they call the troposphere. And the farther up you go, you drop in temperature like crazy. Okay? If you've ever been in a flight, jet flight, and you've seen all the little screens they have up there, they'll give you the outdoor temperature. You don't want to go there. It is extraordinarily cold. Okay? So the troposphere, if you get up, you see near the surface, you have all sorts of thermal currents going on. You may be warmer aloft than you are down low, and maybe cooler. I mean, so in here, everything's sort of mixed up. But after you get to a certain point there, wherever that point is, then the temperature starts dropping. Very cold, extraordinarily cold. It looks like maybe minus 40. This is Celsius. It's really cold. About minus 40 Fahrenheit too, by the way. Okay. Then you enter what they call the stratosphere. And you have certain types of clouds they call stratus clouds. They're way up there. And it stays cold, but it levels off. And is almost constant for a while. But then somewhere up there in the stratosphere starts warming again. Okay? Doesn't get extraordinarily warm, but it gets above freezing. So you're back up, above freezing again. And that's about 50 kilometers up, which is about 40 some miles up. So you're way, way, way up there. We don't go there, okay? That's the stratosphere. Then you enter what they call the mesosphere, which you start dropping again and get way colder than you did before. In fact, somewhere down closer to minus 100 degrees Celsius. And then you get into the thermosphere, and what in the world's happening here, folks? Now all of a sudden you start warming a little bit at first until you get about 100 kilometers up, which is about 60 miles up. This is way up there. And then the temperature just shoots up like crazy. That's what they call the thermosphere. It goes up well over 200 degrees Celsius. Looks like it's approaching 300 degrees Celsius. May even exceed it. I don't know how far it goes. But now they did something intentional here. Notice they have darker blue here and lighter blue there. It sort of indicates the higher you go, the thinner the atmosphere gets. Farther apart from molecules. You're not going to live up there. You couldn't possibly exist up there because it's just not enough density. You would explode. The pressure is too low. So you'd have to have on a pressure suit. But now, that's some real world modeling, and those are continuous functions. Now, you say, wait a minute, but it would have to be continuous. Even though it's moving around like crazy, you can't go anywhere and just suddenly have a jump in temperature. It's going to be maybe a sharp change, but it's still going to be a continuous change. You can't just pass a point and all of a sudden your temperature jumps. It changes rapidly, but it is always continuous. So even something like that, I can't write the equation that would do that. I guess someone could, given enough parameters, but no, okay, I don't even want to. Here's another example of real-world modeling. And this one's much more reasonable looking. World population. 1750, we're at, this is in millions of people, still less than 1 billion, because 1,000 million would be a billion. So we were less than a billion at that time, 1750. And then it was growing, frankly, significantly. Look at what happened since 1950 to 2000. Ooh, can't continue that forever. Guess what? Our planet can only be and support so many people. But look at those numbers. Okay? Now, why would that be? Anyone think of any reasons? Okay, blame it all on us here. Okay. That's part of it here in the U.S. would for sure that increases big time. But here's what I think: we got better health, wiped out a lot of diseases. Okay, more immunization programs, and this sounds bizarre. We got nitrogen fertilizers. Because without being able to grow the food, can't support the population. So what happened in the 1940s was a guy from Germany named Franz Haber developed a technique to use methane gas, which is a greenhouse gas, it's what you use in Bunsen burner, like propane. It's only slightly different methane. Taking methane gas and either elemental nitrogen from the atmosphere or nitrous oxides. I mean, there's nitrogen in this room. Guess what? The percentage of the nitrogen is in this room.
Probably in the 90 percentile.
A little less than 80, but still huge. We've got plenty of nitrogen everywhere in our atmosphere, but none of that is useful for fertilizing crops.
Isn't it like the second most abundant element in the universe? Like second to like hydrogen?
I don't know that. I don't know the answer to that one. I know in our solar system, we're one of the few planets that have significant nitrogen in our atmospheres. Some of them have no atmospheres or largely carbon dioxide, methane, other stuff. We have nitrogen. And thank you, whoever decided to put it here. Fantastic. I appreciate it. It doesn't hurt us, doesn't help us any, but it's the good news is we have oxygen, and most of the others don't either. But the reason for that is those nice little green plants out there. All the atmospheres that have atmosphere have carbon dioxide in them. They have excess carbon dioxide. Nothing can live there unless you have plants. We're the only planet with green plants, and therefore we have oxygen that we can breathe. Okay. But Franz Haber came up with a way to take nitrogen gas, I think it was, and methane, heat it, very high temperatures, pressures, and stuff like this, and form ammonia.
I can only imagine the failed experiments.
Yeah.
Because methane's so flammable.
Yeah. And because of that, we have the Green Revolution, that we can feed tons more people, because nitrogen fertilizer is the number one need for fertilization is the nitrogen. To make our proteins, you have to have nitrogen. So my question to you is, I'm sorry, we're off calculus now, but I think it's important. Do you think Franz Haber received a Nobel Prize for that?
Probably not.
Why not? Isn't that one of the most incredibly important discoveries in chemistry that's ever been made?
Yeah, but I'm just guessing he wouldn't have gotten. He probably lost out to someone. I don't know. I'm just guessing. I'm guessing.
Say again?
I'm just guessing.
Kind of. Franz Haber did a lot of more chemistry in his lifetime. Okay, let me back up. 1930s and 40s German chemist.
Okay.
He's the one who developed gases to kill people in the concentration camps. He experimented on people, seeing what these various poisons would do to them. He was one bad dude, Did a fantastically great thing here, but the rest of his memorable career was spent doing really evil stuff. No one wanted to touch him with a 10-foot pole for any award, even though that's probably one of the greatest discoveries ever made. Strange. So yeah, did they not give him what he deserved, or did they ignore him like he deserved to be? I mean, I don't know. Sorry. That's neither here nor there. Number one, we can't sustain that. Okay? Not even with nitrogen fertilizers.
I got to tell you this too, since we're already off
Yeah.
tangent. Hydrogen, most abundant. Helium,
That's in the universe.
Yes.
Yeah, right. Yeah, and I knew hydrogen and helium were, because most stars are made up of those. And when they fuse, they become carbon. When hydrogen fuses to helium, helium fuses to carbon. Okay? And then was iron in there?
Iron.
Yeah. Iron is at the core of most of your solid things, because when ultimate destination of carbon fusion ultimately becomes iron. So that's why those are there. The others are incidental. Yeah.
Is there a limit to the elements we have?
Limit to what?
To the elements.
Good question.
Do they find more elements? Or?
They have blanks on the periodic table, but even the highest numbers on the periodic table, even though they have some elements there, they have some really strange names that most of them seem like they're unknown, or something like that, ammonium or something like that. The thing is, those way up there, they do think they have isolated them, but for brief times, because after I don't have my book in here, 98, 96, somewhere up in there, about uranium or a little beyond uranium, most of the ones are unstable. In other words, they're such big atoms, they radioactively decay. Some of them in milliseconds or microseconds. They have detected, they have seen it for an instant, but it immediately decays to something lower down. So I don't know if there's a limit to how big. Right now it seems like to have stable ones, it does seem like there may be a limit. But maybe that stability in our reference frame, maybe some other parallel universe that would be stable. I don't know. That's beyond what I can grasp. All right, you want to do preliminary questions? All right, let's do a few. Let's see. All right, let's do this one. Which property of f of x equal x cubed allows us to conclude that the limit as x approaches 2 of x cubed is equal to 8. What property allows us to do that without doing a bunch of calculations and second? Yeah. What allows us to substitute? What is the prerequisite before you can substitute? The function must be continuous at that value. That the property is x cubed is continuous everywhere. So if you're trying to take the limit of it, plug it in. Okay? Now that's my perspective on it. Let's make sure we're agreeing with the book. This is 2.4 preliminary question. Continuity. Got it. Number 2. What can be said about f of 3? This is a different problem here. F of 3. If f is continuous, and the limit as x approaches 3 of f of x is 1/2. Now, the question is, what can be said about f of 3? That's the question. If these two things are true, f is continuous, and the limit of f of x as x approaches 3 is 1/2.
I guess if they're trying to get to where that they can both exist, I mean, they're not going to overlap. Correct? I mean, is that kind of what they're getting to? Or?
Kinda. I think you're making it a little harder than it is.
Okay.
If here, that one of those there, fourth or maybe, if alpha is continuous at x equals 3, and this is as it's continuous everywhere, then the limit as x approaches 3 of alpha of x is alpha 3. Right? So therefore, alpha 3 is 1/2. That's all they're getting at. Yeah.
Okay.
That's it, exactly.
It's a little roundabout.
Yeah, it's around their elbow to get to the ear. You know. So let's make sure that's what they're getting at. That alpha 3 is equal to 1/2. That's all they're saying. Yeah. Okay. Number 3. Suppose that alpha of x is less than 0. So here's your given, alpha of x less than 0. Okay? We know that. We know that if x is positive. If x is greater than 0. Okay? And we also know that alpha of x is greater than 1 if x is negative. So that means less than 0. Okay? Can f be continuous at 0? Can f be continuous at 0? So f is negative down here, down here, for everywhere the x is positive. Everywhere is positive. Okay? F of x is greater than 1 for everywhere the x is negative. Not just positive, but greater than 1. Can f, what's the question? Can f be continuous at 0? X equals 0. No way. This would be fine. If it's negative everywhere the x is greater than 0, it could be approaching 0. Alpha is less than 0, but it could be approaching 0 there. But here, the best you can do is be coming down toward 1 for x negative. That limit and this limit, the best you can do, they can't get, they're not close. So no. Does that make sense? Okay. Probably should have drawn something rather than wave my arms. People listening at home will say, what is he talking about? You should be here. No, I didn't say that, did I? Okay, no. Okay. I didn't say that. Okay. Number 4. I'm going to start with clean page here, I think, because that's getting sort of crowded. Okay. Number 4. Is it possible to determine alpha of 7 if alpha of x is equal to 3, okay, for all x is less than 7, okay, and f is right continuous at x equals 7, and f is right continuous at x equals 7. Okay. Is it possible to determine alpha of 7 if alpha of x is equal to 3 for all x is less than 7 and alpha is right continuous at x equals 7? Okay. I guess I will. Okay. So 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. This is where our interest is, x equals 7. And we know that alpha of x is equal to 3 for all values less than, for x less than 7. And we know alpha is right continuous at x equals 7. Right continuous. They don't say what it is at x equals 7, but it's right continuous. That means from the right-hand side, it's coming down and is continuous. But it doesn't have to be at 7. So I would say the first part of that is no. is it possible to determine what f is at 7? If it's 3 for all values less than 7, but right continuous to x equals 7, I would say the answer has to be no. Let's see what they say. Number 4 says no. But on the other hand, it says, the second part of that says, what is f is left continuous? Well, basically, it just told us it was left continuous, okay? If f is left continuous, meaning that all the values going into there is approaching, then, and it says at, not approaching, but if it's continuous at x equals 7, that means left continuous means the value it's approaching is the value it is. Okay? So these were saying right continuous. They could be here, 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 or anywhere down here. I mean, way down here. You know, just approaching something. But unless it happened to be coming in there, we don't know the value. But if it's left continuous, that means that's what it is. Okay, at x equals 7. All right, so that was, the second part is yes. So it's a no yes. How about number 5? Are the following statements true or false? And there's 5 of these, so I'm going to write these on a clean page. Okay. Are the following true or false? If false, then draw or give a counter example and state a correct version. Okay? So let's do A. A says f is continuous at x equal a. Okay, now what does that mean? For f to be continuous at x equal a? F of a is the value you would expect it to be. I mean, you can write that down. Okay, f is continuous at f equal a if the left and right hand left and right hand, that's my lousy abbreviation, limits, okay, of f of x, okay, as x approaches a, exist and are equal.
I know it's easier seeing it.
Okay? Now, is that statement true? The f is continuous at a if the left hand limits and the right hand limits as x approaches a both exist and are equal to each other.
Is that true?
Yes, it's got to be true.
Because
If
the
they-
continuity at a point definition.
So again?
Is that the continuity at a point definition?
Yeah, I think so. Yeah. Okay. So that one hopefully is yes. Let's make sure. Oh no, A is false.
Oh,
Wait a
really?
minute.
Continuity at a point.
Oh wait, yeah, okay, right. I was starting to say this, but I thought that included it. It doesn't. Okay. The left hand and right hand limits do exist. Okay. And they're equal to the same value. But the part we left off was they would be equal to f of a. Okay. And here's the picture that would show that. Okay. What if you had a function that's doing this here? Here's your graph. Here is a here. Okay. The limit is f approaches a from the left and f approaches a from the right are exactly the same. They both exist. They have the same value, but f of a is up here or down here or anywhere other than that, then that would not be the case.
Oh my goodness.
Okay? And not only that, if you had an open circle there,
Yeah.
then f would not be continuous at a because f of a is not, f of x is not f of a at that point, okay? Because if it doesn't exist, it can't be. or if it's some other value other than what those equal values would be. So yeah, you would also have to have the statement in f of x, the limit exists and is f of a. You would have to have that statement in there. Okay. Now, B. Yeah, I don't like these too much. The B one. F is continuous at x equal a if left and right. Okay. F is continuous at x equal a. Same thing as we have it there. F is continuous at a if the left and right hand limits of f of x as x approaches a exist and equal f of a. All they said before was they both exist and are equal to each other, but it didn't say and are equal, but it says both exist and are equal to f of a. That, I think, covers
This one's true.
Yeah. If the left and right hand limits of f of x as x approaches a from left and right both exist and equal f of a. That one I think has to be. B is true. Got it. Okay. Let's look at C. Now this is B was almost the same wording, except here it was not just exist and are equal, but exist and are equal to f of a. That made it true. The C one. If the left and right hand limits of f of a as x approaches a exist, so here we're starting differently. If, actually it's almost the same, left and right hand limits, okay, of f of x as x approaches a, okay, if these both exist, okay, then that's the given. Here's the result. F has a removable discontinuity at x equal a. F has removable discontinuity at x equal a. Okay.
That would be false.
Let's see. If the left hand and right hand limits of f of x as x approaches a exist, okay, all it takes is for them to exist, then f has removable discontinuity. Yeah, you're right. It is false.
Kind of similar to what we drew.
No, not that one. Okay? That would be this one's coming here and that one going there. They
Okay.
both exist. Both of them exist
Gotcha.
at x equal a, and no removable discontinuity is going to make it. If they exist and are equal to each other, then, yeah, then a removal. If it has a discontinuity there, it's removable.
So a discontinuity is actual space between two, rather than just the hole.
A hole is a discontinuity, but also space is.
Okay, so
But
that
also
that
this
would be
is.
considered.
What's that?
Would that not have been considered a discontinuity with the hole right there? You see what I'm saying? I was asking if how we had it going with
Okay.
a hole in it.
This would have a removable.
Okay.
If that was anywhere else, that would be a removable.
Okay.
But if they were not coming to the same point, that would not be a removal. It would be a discontinuity, one you couldn't remove.
Gotcha.
Now, also, an infinite discontinuity, of course, it's not removable because they never. I guess they get closer and closer to each other, but they don't have any value that they could ever come. Yeah. So C was false. The correct statement is if the left and right hand limits of f of x as x approaches a are equal, but not equal to f of a, then it has a removable discontinuity. Okay. Now, D. I think I'm going to have to go to a clean page because I can't write any more at the bottom there. The D one. If f and g are continuous at f of a, f and g continuous at x equal a. Okay, got it. Then f plus g is continuous at x equal a. What you think?
I think it's true because of theorem 1.
Yeah, exactly. That's one of your limit. The sum of a limit is the limit. Yeah,
Yeah.
that certainly.
Basic laws of continuity.
Yeah.
If f and g are continuous at x equals c, then
Right.
the following functions are continuous f plus g.
Exactly. So that's true, and that's all they say is true. Okay, E. If f and g are continuous at x equal a, same thing here, all that's the same, then
F over g
f over g,
is continuous at x equal a.
yeah, and that's all the rest of that is the same. True or false?
Well, it looks like it would be, it's right here,
Yeah,
same theorem,
but you have a
it can't
caveat.
be equal to 0.
G cannot equal 0.
Yeah.
If you put that in it, it's true. Leaving that out, it's not always true.
Right.
Okay, that's it, exactly. So,
True, but g
false. The
can't
correct
equal-
statement is f and g are continuous at x equal a, and g of a is not 0. Then that's true. So you have to have that caveat in there. All right, homework exercises here. Do number 1. Do number 3. Do number 5. Then do any of the odds 7 through 15. Any of the odds 17 through 33. Any of the odds 35 to 47. Then do 49. Do either 51 or 53 or both if you choose. That's up to you. Do 55. Then do either 57 or 59 or both. That's up to you. And then do 61. Either 63 or 65 or both. And then any of the odds 67 to 79. Okay? And then you can look at 81 through 85. Some of those are proof, well, I don't know, yeah. Some of them are proofs, some of them are take off some things. So take a look at those, read through them if you want to spend the time doing them, but don't get bogged down. All right, good deal. Let's move on to, do we have time? Yeah. Well, we don't have much time, do we? Sorry. 2.5. Okay, let's see, we end at 11:10. It's almost there. Almost there, 11:09. Let's see if we can at least introduce it. I don't know why it's not opening though. This thing is it's been so terribly slow today.
Evaluating limits algebraically.
Yeah, which we've been doing. Okay. Well, I think, yeah. While we're waiting for this open end, we'll begin at the beginning of 2.5 next time. It finally now maybe is about to open, but we're out of time. All right, sorry about that. Wish we'd have gotten a little further. We'll do 2.5, 2.6. We'll go through 2.7 quickly. We'll not spend a lot of time on that. And we'll do 2.8. And then we'll do 2.9, which back when I took calculus, that's where you began, okay? None of this, I didn't like it that way. I like this way a little bit better. Okay, but yeah, so we'll go from there. Hopefully we'll move along. Some of these sections coming up are pretty short, so hopefully we can get through them a bit more quickly. All right, yes?
Kind of are projected, like, are we still kind of in line as?
I think we're doing okay. The only trouble is we started a week behind, basically.
We're on
So I don't know if we'll ever catch up that week. So we're about a quarter way through the course, you know. So we're doing chapter 2, 3, 4, and the first part of 5. So we're not far back. Yeah. Okay. All right. Good deal. We will see you. I don't see any of you anymore. Rodney, I don't have you for another course, do I? C terms lately, I only had you once, right? Right. Yeah, right. Okay, well, have a good weekend then.
Yes.
My other 3 classes that I do on Monday, I see everyone in those classes in one of the other 3 classes. It's just bizarre. I think it's that way. Pretty sure it is. Rather bizarre. All right, have a good weekend.
Thank you, you too.
Okay, I don't want to do that. Oh, let me end this.